Hi everybody, Physics Ninja here. Today I want to look at a problem of a charged particle between parallel plates. I previously did a video similar to this one, except the charged particle was kind of coming in from the left and moving horizontally through the parallel plates. If you want to look at that video, I'll put the link in the description down below. Today, however, we have a different problem. Actually, this problem is a little bit easier than the previous case. What I'm going to do here is I'm going to take a charged particle. In this case, it's going to be a proton, and I'm going to shoot that proton upward, and I'm going to shoot it so that it goes through this tiny little hole. And when doing so, it's going to enter a region where there's an electric field produced by these parallel plates. So I have just a basic question. What's the minimum speed over here that you have to launch it so that the charged particle basically just goes up and just touches the plates before coming back down? Okay, what velocity do I have to give that proton in order to just make it to that positively charged plate? So we're going to look at this problem using two different techniques. We're going to first look at forces acting on it, calculate the acceleration, and then do some kinematics to solve for this. And then I'll also solve the problem using energy and conservation of energy. All right, remember, like with all my videos, give it a thumbs up if you like the video. If you don't like it, don't do anything. And consider subscribing to my channel. If you have any questions, leave them in the comments section. I'll promise I'll get back to you. All right, let's get started. All right, here's some of the key information for this problem here. So we have a charged particle. In this case, it's going to be a proton. If it's a proton, we know the charge here is given by 1.6 times 10 to the negative 19 coulombs. And it's a proton, you just look up this number. We also know the mass of that charge, which is 1.67 times 10 to the negative 27 kilograms. Now I've got parallel plates that I've previously charged by connecting it to a battery. And the separation between the plates is 1 centimeter. And I have a certain amount of charge here, positive charge on one plate, negative charge on the other plate, such that the electric field produced by these charges over here is 10,000 newtons per coulomb. All right, the first thing to consider is what happens when this charged particle is moving upward over here, and it's going to enter the field region over here. At some point, the charged particle will enter this region over here. Now, what happens when this charged particle is in the field region? The first thing you have to do is, let's do a free body diagram, okay? Just see what are all the forces acting on this charge when it's in this electric field. Okay, so the free body diagram for this proton here is pretty straightforward. Let's just draw the proton over here. If you look at it, first of all, this is a positive charge, right? It's a small positive charge, little q. And when it's in that field, first thing you have to realize is there's going to be an electric force acting on this charge. Electric force is a vector, and that vector is going to point downward because it's being repelled by the positive charge over here, and it's being attracted by the negatively charged plate. So the magnitude of this electric force is given by QE. All right, and that's really important. And the force is in the same direction as the electric field in this case, because this guy here is a positive charge, right? So we have two vectors that are in the same direction. The next thing you do now is you apply Newton's second law to this problem. And Newton's second law says you add up all the forces acting on that charge. In this case, all the forces are in that vertical direction here, and there's only one force. So when I add them all up, it's simply the electric force. And you add them all up, that has to be equal to the mass times the acceleration. And that means that, well, hey, the acceleration is going to be in the same direction as the electric force. So the the acceleration in this case, we can get the magnitude of it. You simply have to divide through by the mass, and let's substitute our value for the electric force. So at the end of the day, what we end up getting is this very important equation over here, is that the acceleration, which is Q, times the magnitude of the electric field, and I end up dividing through by the mass over here to isolate the acceleration. And this is what I'm left with. Now, we can actually get a number for acceleration here. And the key point about this guy here is going to be in the same direction as the electric field because the charge is positive and mass is always positive. So really the direction of the acceleration here, this is in the down direction. All right, the other important thing to consider about this problem is this guy over here, right? The electric field for this problem is constant, right? This is a constant, which means it's uniform, right? And if we're between these parallel plates, the electric field is pretty much uniform. So that means that this acceleration here is also constant. A is also constant. And the reason that this is really, really important for this problem is that if the acceleration is constant, we can now do simple kinematics. So let's go ahead and set up some kinematics for this problem to analyze the motion of the charged particle between the two parallel plates. So we're going to have two important kinematic equations here. Again, our acceleration is constant. Here's the magnitude. The direction we know is down. So the kinematic equations are going to be number 1 and number 2 here. Number 1, let's just look at the vertical displacement of this charged particle. So that's the y position. Y position is going to be equal to y0 plus the initial velocity multiplied by time. And I'm just going to stick a negative front in the front of the acceleration term because it's slowing down and the acceleration is down. It's in the down direction, and I'm defining that down direction to be the negative direction. All right, this is my coordinate system here for this particular problem. Everything pointing up is positive, everything pointing down is negative, so I've just taken that out of the equation. The other thing we need to know for this problem is what is the velocity of the charged particle, right? When it enters this field region, its velocity was initially going up, but since the acceleration is down, that means that the charge will slow down, okay? It's going to slow down. And the expression for the velocity is simply going to be like this, the initial velocity. And again, I'll just take the negative sign out, multiplied by acceleration times time. And now you could see that having this negative sign here is really going to make the velocity kind of slow down as time increases. All right, so we have our two equations. And now what we want here is we want our maximum displacement in the y velocity. We actually want the charged particle to actually come and just touch the plate and then come back down like this. Okay, so what we want here really is that our y displacement for this problem, this is what we want. We want delta y, which is my final minus the initial. We want this to be the spacing between the plates. Okay, that's really important. And the other important thing to do is if we want the charged particle to reach this point, there's also something else that's going to happen here. So what happens is it's going really fast. It starts to slow down, slow down, slow down, up until it reaches this point. At this maximum y displacement, we want the vertical velocity here to be equal to 0, right at the turnaround point. And then after, it's going to start speeding up. It's speeding up in the down direction. So right at this point here, this is a really important expression here, is that our vertical velocity has to be equal to 0. So now if we go back here and consider our equation 2, well, if you substitute now Vy is equal to 0, what you can do is you can find how much time it takes for this charged particle to slow down and to reach this point over here. So let's go ahead and do that. We can calculate that. And what you're going to find here, so go and substitute it into equation 2. We want 0 equal to my initial velocity and minus the acceleration times time. And now what I do is simply substitute the expression for the acceleration. That expression for acceleration was the magnitude of the charge, magnitude of the field divided by the mass, and multiplied by the time. So at the end, the time for the velocity to reach 0, you simply have to do a little bit of algebra now. Bring this on the other side and divide through by this term here in the bracket. I'm going to rearrange things a little bit, and my expression is going to look like this. So this is how much time it takes for the velocity to be equal to 0. All right, the next thing we want to do now is, well, we know what our vertical displacement is. All we have to do now is go back to equation 1. We have the time now that we could substitute in here, and my goal now will be simply to solve what is that initial velocity so that it makes it all the way to the other plate. So let's go ahead on the other page and do this math. All right, the next thing we wanted now is we wanted our vertical displacement. Let's rewrite equation 1 over here. This tells me my y position equals the initial position plus initial velocity times time, and again, minus 1/2 at squared. And really what we want in this case, we want our delta y to be equal to the spacing between the plates. So let's go ahead and do that. If we do that, just bring this guy on the other side, and that becomes delta y, right? Delta y is always a y minus some initial value. So let's simplify equation 1. So we get that the distance between the plates, and this is really what we want, time minus 1/2 at squared. Now, the next thing we have, remember, is how much time it takes for when the velocity equals to 0, right? And we just want that charged particle to reach the other plate. So all you have to do now is simply substitute the time for our expression up above, okay? And you can also substitute acceleration. For now, let me just kind of do it this way. Let's go over here. So we have the distance between the plates. I'll just keep the Vy over here. And for my expression for time now, rather than doing the second expression, let's just start off with just this one. V0 divided by the acceleration. That'll make the math a little bit easier. We won't have so many variables to tackle over here. Let's keep acceleration like this. And now we have this t squared. And t, again, is initial velocity divided by acceleration. And we square that term. Now you do a little bit of algebra. What you end up getting is you get V0 squared divided by A. And then minus 1/2, and if you look at this other term here, this becomes A, and this becomes V0 squared, and this becomes A squared. Now have a look at this term. You have an A here, and you have 2 of them over here, so you can get rid of 1. And these 2 terms are exactly the same, except the second one has a coefficient of 1/2 in the front of it. So at the end, this is our expression for our displacement, is 1/2 V0 squared divided by acceleration. All right, and remember our problem, right? The acceleration for this problem, we know what it was. The acceleration was pretty straightforward. It was the charge multiplied by the electric field and divided by the mass. And rather than putting the mass kind of down below, if I'm dividing, I could just bring it to the top over here. And this is my final expression over here for the distance between the plates, which I know. So the only unknown now in this problem is, what is V0? So we have to do a little bit of math over here. Just isolate the V0. You bring a couple terms over to the other side, divide by the mass, and then take the square root of everything. And this is what we end up getting. So V0 end up the square root of a whole bunch of different terms here. So we get 2Q, the distance between the plates multiplied by the electric field. And all of this gets divided by the mass. All right, here we have it, folks. So this would be the velocity, such that if you give that charged particle, that proton, this velocity over here, you're going to end up that the charged particle is just going to make it to the other side. Okay? So all you have to do now is simply substitute in the numbers. So let's go ahead and do that. You substitute the numbers over here, we get kind of a big expression. We get 1.6 times 10 to the negative 19. The distance between the plates was 1 centimeter. So this is 0.01 meter. What else? The electric field was 10,000 newtons per coulomb. That's already in SI units. We don't have to convert anything. And the last part here was the mass. The mass is 1.67 times 10 to the negative 27 kilograms. Put all of that in the calculator. You should get something like this, 1.38 times 10 to the 5. And again, that will be in meters per second. All right, I have everything here in SI units. So if that charged particle has this particular velocity here, which is just a number here at the end of the day, it's actually going to just make it to the other plate and then turn around and then come back. All right, let's go ahead and see how we can set this problem up now using conservation of energy. All right, to solve this problem using conservation of energy, let's consider that this bottom plate position is going to be my initial position. And this top plate here is my final position. And what we have here is that the total energy at this point has to be equal to the total energy at my final position. So initially what we have is a lot of kinetic energy, and we're going to be moving in a region where there's an electric field. Guess what? We're also going to have some electrical potential energy when I first enter this field region. And as I move now toward the other plate, and once I reach the other side, and if I just kind of turn around over here, that means that my velocity or my speed is 0 once I'm at the other plate. So my final kinetic energy over here at the top, K final, that one's easy. That has to be equal to 0. And that energy had to go somewhere. So actually, it's going to be converted into electrical potential energy, which I'm going to call U final. So the initial kinetic energy is really straightforward. I simply have a charged particle, a proton that's moving. So that guy's always the same thing. 1/2 the mass of that charge multiplied by that initial velocity. And let's just rewrite all of these other terms. and U final. So there's no final kinetic energy for this problem. So all we really have to do is evaluate what is this potential energy over here. All right, potential energy, if you remember now from your class, you probably saw that the potential energy of a charged particle, in this case the charge is Q. Remember, this little guy over here had a charge Q, and I'm placing it now in a region where there's an electric field. The amount of energy that a charge has when it's in a region of electric field can be written as this. It's the charge multiplied by the value of the electrical potential, right? So this guy here is electrical potential. This is the value of the charge, and this is how much energy you have, at least potential energy. So our goal now is, well, we need to calculate what is this value. What is the value of V when I'm close to this plate? So what is the value of V initial over here? And what is the value of V final? If I know that, I can calculate both of these potential energy terms and then simply solve for that initial velocity. So careful here, I'm using an uppercase V to note the electrical potential versus the initial velocity here, which is lowercase v0. All right, so how do we relate that? And this is pretty simple for parallel plates. Okay, so I'm going to write this down. The expression that I'm writing down here is only valid for parallel plates. So don't try to use it for point charges. Don't try to use it for cylinders. And for this case, it's pretty simple. It simply says that, again, remember, how would we actually obtain the system? We would plug it into a battery, right? You'd plug it into a battery, and the voltage difference between the battery I can write as V final minus V initial. This is the potential difference of the terminals of this battery. That there simply equals to, and I'm just writing it as the magnitude here, as I call this Eds formula because it's simply E, the magnitude of the electric field, multiplied by the distance between the plates. So in this case here, if I have 10,000 newtons per coulomb, and the distance between the plates, I had previously said that the distance between the plates, we call it D, and that was 1 centimeter. So if I go ahead here and multiply this by, convert it to meters, what you end up getting here is 100 volts. That's the difference of potential. So that might mean here that the difference has to be 100. So you might have this one here at plus 50 volts, and you might have this one here at negative 50 volts, right? So that would mean that the difference, V final minus V initial over here, 50 minus 50 would give me 100 volts. So now let's go ahead and do that. Just substitute our values over here. Let's go back to the expression for conservation of energy. And all we really want to do now is substitute our expressions for the electrical potential energy. So we have our kinetic energy, 1/2 mv initial squared. Now the initial potential energy as I enter the field region is the charge Q multiplied by the value of that potential. Okay. And that there has to be equal to the final potential energy. So it's the charge Q minus V final. Now you have to do a little bit of algebra because our goal was to find how fast do I have to put this charge in the field region. So let's go ahead and do that. So I'm going to bring this term on the other side. So this becomes Q. This is V final minus V initial. Right? This is the difference of potential between both of those plates, which we just said was 100 volts. And all of this here has to be equal to my initial kinetic energy. And now again, you do a little bit of algebra because my goal was to find V0. So there's going to be a square root term over here. Oops. We're going to have the square root. I bring the 2 over next door. I get 2. Q, the difference of potential. Let's just call that delta V. And again, divided by the mass M. Now this expression might look a little bit different from the previous one because the previous one, remember, I had it in terms of the electric field and the distance D. However, that's what this guy is right here. So if you go back and you substitute that, you're going to get the exact same expression as we previously had. And that one, I know the value. You substitute all these values here, you're going to get 1.38 times 10 to the 5. And again, that is going to be in meters per second. I'm working in SI units over here. And that's it. That's how you would do this problem now using conservation of energy. I think the key is really just finding what this difference of voltage is between the plates. And you can do that using this Eds formula, what I call. And again, the key to remember here is that this formula here is only valid for parallel plates. If you have different systems of charge, for example, charge cylinders, the expression is going to look a little bit different than this simple expression. The reason it looks so simple for parallel plates is because the electric field is uniform here. So that means that the voltage varies linearly with distance between the plates. All right, I think I've said enough about this problem. Again, just leave a comment if you have any questions. I'll try to clarify something if it's not clear. All right, have a great day, folks. Thanks for watching.